Okay, so now we are going to learn something very interesting. What are the properties of materials? So if I ask you, you need to define all the properties of all the materials. What is the definition of the word properties itself? Then what are you going to say? Okay, well, you know that different materials behave differently under certain conditions, specific set of conditions. So for example, I start heating a material. So some materials will melt, or some materials will conduct the heat. Some materials will not heat up at all, so they will be thermal insulators. Also, in a given range of temperature, you will have a different, response from the material. And then let's say if the temperatures are too high or too low, you may get different type of response. Similarly, for example, when you know about stress or mechanical properties, in a certain range of forces or loads, you have linear response from the material. Stress is proportional to the strain. But in another, afterwards you will have, maybe the material will fracture or the material will not behave linearly. So what is property? Again, property is nothing but the response from the material. So response from any material to what? To a certain field. So let's say to a certain field or to a certain force, applied force. Okay, so now we can have different types of forces. We can have electrical forces, magnetic forces. So we generally would use the term field for all of these things. But let's say there is any external field. Now my material gives a response R. So how do I define R? This R is basically nothing. This is a function of your whatever field, external field you have applied. So this is basically the definition of the property, but let's get into it a little bit more, because the response, as I already told you, may not always be linear. Also, at different fields you will have different kinds of responses. It may be linear within some range, in some range, and not in the other range. Okay, so how do we expand something mathematically? One thing that comes to your mind, something very simple, is the Taylor expansion. Okay, so I'm going to write, how do we do the Taylor expansion? Although most likely you remember it, but I'm going to write for any given function, say f, which is a function of x. So what is the simple expression for Taylor series? We know that it is, whatever was the function at 0, and then we do a summation of, for say n values, so n equals 1 to say infinity, and then we take the derivative. So this is your nth derivative of the function with respect to whatever is your x, and we are doing this entire thing at x equals 0. Okay, multiplied by x to the power n. So this is your Taylor expansion. This is the Taylor series. This is your expression. Okay, so now let us try to also express our material response in terms of the Taylor expansion. Okay, so how do I write that? Let's say this is my response R. Okay, R will have some response at without any field. So 0 means without any external force or field, and then you can now write down a couple of terms. Let me write down let's say 2 or 3 terms. So I'm assuming that my response does not depend on anything other than the field at this point. So I'm not taking the partial derivative. So this is at f equals 0, and then the second term will be 1 divided by 2 factorial, and the second derivative of your response, and so on. Okay, also in this case we will have multiplied by f, and in the second derivative f square, and so on. Okay, so this is your Taylor expansion of the response of your material. Now there are a couple of things here. First of all, before we go into the terms later on, the higher order terms, let's see what is R0. So R0, you can see that this is nothing but the response of the material when the field equals 0. So basically there is this is like the intrinsic property of your material. So when do you have the intrinsic property? Let's say we take a couple of examples. We take the example of thermal conductivity. Okay, so thermal conductivity of a material will show the response you will see only when the material heats up, right? Which basically means that you need to provide some heat, and So that is your field here. R0 basically means your heat equals 0. So you're not providing any external heat at that given point, which basically would mean that at that point there will be no response from the material. So in this particular case, your R0 is 0. However, if we take another example, let's say magnetic properties of iron or any ferromagnetic material. So for any ferromagnetic material, then what happens is, even when there is no external magnetic field applied, there is some value. There's some R0 value is there. So it is a non-zero value. Okay, so these are the two types of responses that you can get when there is no external field. Okay, so what we are going to do is we are going to keep this particular term, and then we will also now move on to the higher order terms. So if in this particular case I assume that my material after first order there is nothing. Okay, so what do I mean by that? This is the first term basically is just your the linear response, but the second and higher order terms basically show the non-linear behavior of the material. So what I can do, I can rewrite this expression as my response equals whatever is the R0, and then just the first term. So 1 divided by 1 factorial is just 1, and then we have our first term dr by df, and this is at f equals 0 multiplied by f. So this is the expression which basically now tells me what is the material property. Now what I can write, this will be this particular term. You see that this particular term is basically the characteristic of my material, and this is what I can simply call the property of the material, or let's say I have just written a letter P here. What does this mean? So now I will rewrite this term. So I can say that my R basically equals whatever was the R0 if it was a non-zero value plus P into F. So this P now is the property. So you will often see these kind of expressions in the case of linear behavior of the material. So if we don't go into the non-linear region, and then what is your property basically? Property is nothing but the response of your material with respect to a certain field when field equals 0. So the 0th term basically. So this is how you define the material property. Okay, now think of one more thing. Is the response from your material same in all directions? So if I have, whatever, some crystal, and I apply a certain force, whatever, or if I apply an external electric field, or if I provide heat, what is the response from your material? Is it same in, let's say, all directions? Or is it different in some directions and different in other directions? Okay. So indeed, there are both types of materials. The materials that offer the properties that are independent of directions. So what do you call them? Direction independent properties. They are called isotropic materials, or the properties are also called isotropic properties sometimes. And of course, then we also have other types of materials which will offer direction dependent properties. And why would that happen, by the way? If you have a certain type of molecular structure, crystal structure, in that case, what you will have is what is known as the anisotropic properties. Now, in the case of carbon, interestingly, you will see the examples of both. Our very interesting carbon material, something that we are going to learn, most extensively in this course, graphite. That is a material which offers anisotropic properties because of its layered structure. So if there is something with layered structure, I apply a force from top, or I apply a force from the from the side, then I'm going to get different kind of response from the material. Similarly, this is also valid for let's say the electrical properties of the material, various other thermal properties even. So we are going to see both types of properties. Now again, how do we go back to mathematically describing these kind of properties? So let's first go back to our usual expression. What was the expression again? We had R equals P into F. And we can also find various examples of these kind of, so this is, if I call this expression 1, let's say we talk about voltage and current. So you know that voltage and current are proportional in any material. But there is some proportionality constant. In this particular case, this is the resistance. So electrical resistance is the property of your, it is the intrinsic property or the characteristic of the material itself. So this is a very, very, very simple example of, linear response of the material. These kind of expressions you have seen multiple times. So in a more general form, let me write it as X equals this P into Y. Okay. Now, the point is, till now what we have considered is X and Y both were scalar properties. So basically there was nothing to do with the directions. But it is also possible that the properties of the material are anisotropic, which means that now your X and Y both have some direction associated with them, and they are both now vectors. P still remains scalar because P in most cases is a number, so it's like electrical resistance. But if you have properties which are direction dependent, in that case, what happens? So what is P, by the way? Here P in this particular case is dx by dy at your y equals 0. Okay, now if I have the direction dependent, in that case I will write Pij, and that would be equal to some partial derivative of xi, let's say, and yj, again equals at y equals 0. So this is now going to be your the other expression for your property itself. Okay, what does this mean? Now you have, how many combinations are possible? Now you have 9 possible combinations of x and y in the I and j directions. Okay, so how do I basically, because why do we have 9 combinations? Because both x and y are vectors. Okay, so let me write down these expressions again. Okay, so here I have written down all the expressions. These are the general expressions which can be represented as a 2D tensor or a matrix. Okay, so now why we are discussing all this? Because in this particular course, we are going to learn about a lot of carbon materials. So I already told you that graphite has anisotropic or direction dependent properties. But there are also some carbon materials, for example, something that we call as non-graphitizing carbon materials. So non-graphitizing carbons, they have, their properties are isotropic. That means they have their crystal structure such that the properties, whenever you apply any particular field, then you see the response in all directions. And also we may or may not be able to go into the details of the mathematical expressions every time, but I hope that from this lecture you will remember how to expand the properties of the material. So when we have the R0 term, when we talk about the response, that is the term which is the residual or the permanent property that we have already learnt. And the first term then expresses the properties in the beginning of your experiment. So when the field is just applied, and that is why we call it field equals 0.